Okay, question and answer 15.1, 15.2, 15.3. Double integrals in rectangles, other rectangularly described areas, and polar described areas. What questions do you get?
Fifteen to question 26.
15.2, 26. Okay, talk to me.
One second, let me check the question out. Yeah, it was more to finding like making okay for the other ones like 25 and 27 or 25. I don't know. They made a little bit more sense. For 26, I didn't know how to do the area kind of confused me.
Okay, so let's start with drawing a picture, because I think that's actually our easiest way to go. We're looking for the volume enclosed by z equals x squared plus y squared plus 1, and the planes x equals 0, y equals 0, z equals 0, and one oblique plane x plus y equals 2. So let me start with what I think are the easy ones. X equals 0, y equals 0, z equals 0. Those are the coordinate planes. So I'm looking at a corner. So now I have to think about the paraboloid and the oblique plane. This equation has a free variable. What does that mean about its graph?
Makes sense. Not all axes.
And the free variable in this case is z. So that makes this a vertically oriented plane. Which means if I think of just the xy plane, then that's a straight line. It's that line. And then the paraboloid, what do we know about that paraboloid? It's upward facing. If it opens upward, it's going to have its z-intercept 1 unit up, right? Right? So there's my paraboloid, my horrible sketch thereof. Right? But I only want the volume under that paraboloid. Wait a minute, where's this line? Right? But that should be a plane that comes up, which means that is going to cut into my paraboloid and cut a section. I want the volume under that piece. Now, I will freely admit, I'm a horrible artist. So let's cheat. Let's boot up the graphing software and draw this there. So I'm going to put in z equals x squared plus y squared plus 1. There's our upward opening paraboloid. And then I'm going to put in x plus y equals 2. Okay, there's the triangle in the x and y plane that we were just drawing. And we want the volume under this surface above that triangle. So if I go back here, this triangle lives here. Now, you'll notice I even cheated. The the capital is in the direction of the y-axis. Capital is in the direction of the y-axis. And then I can say, okay, do you want to do this as a type 1 or a type 2 region? You've got a roof and a floor. So that's the height of your little column. It'll go from the z equals 0 to the z equals here. And then you have to decide how we're going to do this. Just like when we did an area, we said we either need the integral from left to right, top minus bottom, or the integral from bottom to top, right minus left. So I'm saying, oh, the top and the bottom now here, the bottom shape, I have to decide how to do that. So tell me, Ben, how do you want to do that shape? How do you want to describe T? Okay, if it's type 1, then the top and the bottom should be equations. And the left and right should be numbers. So in my little head, I say, oh, I'm going to go up and down first. What's the equation to the bottom? What's the equation at the top? It's the equation for our line rewritten. And then your x bounds. And that means that you're going to do this dy dx. You can do it as a type 2 region and do a dx dy. All you have to do is rearrange the equation the other way. You get to decide that. And that additional freedom comes with its own hang up, which is going to be easier is completely unknown at this point.
When you do the front integral in Z, do you have to do it?
I don't have an integral in Z. I don't have a dz. That's a triple integral. We haven't done those yet. Yeah, we think of volumes the same way. We'll figure out how to do those. We don't know that yet. That's why I have right here, the Z part is already included in here. Z at the top, Z at the bottom. Well, now that I've got my bounds, the outer integral is 0 and 2. The inner one is 0 and negative x plus 2. Top equation minus the bottom, but the bottom is z equals 0. And then this is dy dx. 99% of the difficulty in these problems is exactly this part. From here on out, this is calculus we know how to do. I'm measuring in respect to y, so that's a number. That's, y squared, that's a number, I'm gonna do that, then I gotta plug in this, and that's gonna be the messy part. But that's just algebra. And in a very real sense, that's why I'm very happy to have graphing devices that show me these pictures. Because it takes a very long time to develop a good three-dimensional imaging system in your own head. So you look at the equation and go, what the hell does that look like? That's a non-trivial process. And it is a process where several of my students have told me, I don't want to do that process, F you. And so they do these strictly algebraically. And as we will see later in our Canvas page, dashboard, Calc 2. There is a paper up here about volumes, about describing the limits of integrals, called Integrals from Sketching Impaired. If you don't want to draw pictures, don't draw pictures. I am a very visual person. I think that's easier to me, but it takes a while to say, oh, clearly, that's always the word that pisses me off. Clearly, this is the picture. Yes.
This was gonna be dx,
Exactly. Because I'd have to rearrange this integral to go first in this direction. And that's an x at the bottom and an x at the top. That means I rewrite this equation, x equals negative y plus 2.
For 15.38, can you just do the bounds?
Region in the first quadrant, enclosed by the circle x squared plus y squared equals 4. The line x equals 0 and the line y equals x. Okay. I'm going to start with a picture. Circle of radius 2. X equals 0 is the y-axis. Y equals x. Wait a minute, I'm bounded by the y-axis and this, so my region is here. Okay. That's a polar rectangle. What's your smallest radius? Yep, and then I go out to a radius of? What's my smallest angle? And my biggest? Ta-da!
Then you do the whole circle.
All the way around. What's going to take me all the way around? You got it. Ben?
Am I gonna get the same answer if I did 0 to pi on 4?
I don't know, because 0 to pi on 4 would give me this region down here. And I don't know if the function is the same. I didn't even write down what f of x was. F of x is 2x minus y. I expect you would not get the same answer, because that's not symmetric in this case. You could, on the other hand, if you really wanted to do, go 9 pi over 4 to 10 pi over 4, that would be the same region, but I'm sure bigger numbers wouldn't help it either. I almost want to say it like I'm in the video game. Now you're thinking with polar instead of portals. I'm also really, really used to working in polar coordinates because most of the work in complex variables is easier in polar coordinates. Most of my research work in complex variables was about the way polar coordinates work and some information that gets lost along the way as you do calculations. And I love this crap. So this is fun to me, but I'm a freak. So we're going to run with that. More questions? Yes.
On 15.2, 50 and 52, switching the order of integration.
Yes. Okay. In both of these problems, we're given an integral one way and asked to turn it to the other one. So you want to do 49, 51, 53. One around those. Forty-nine gives me the integral from 1 to 2 and 0 to log x of some function. They don't even tell me what function. Oop. Which really means that all I am concerned about is the region. I'm not actually doing the integral. I'm just drawing the picture. So let me turn this into a set of equations like this. So Nora, this is the y part, and this is the x part. What's the graph y equals 0? And then the graph y equals ln of x. Right? I want x to go from 1 to 2. Where on that curve is x equal to 1? Right. So this is 1 right here, and this is 2 out here somewhere. And that means the region we are interested in is this region. So far, so good? I now want to think of this same region the other way around. So I'm going to take those equations that are in y equals and rewrite them to be in x equals, if I can. Y equals 0, there's no x involved there, so I can't really do anything with that. But this equation, y equals ln of x, how could I write that? How to get rid of an ln? Exactly. Now, here's where picturing the way we are slicing helps. We were doing this dy dx. Now I want to do it dx dy. Functions on the top line, numbers on the bottom line. So let's think about the x, the left side and the right side. What's the equation for x equals on the left? Wait a minute, that would be if I was going straight up and down. I'm looking at this curve on the left, aren't I? What's the equation here, x equals, on the right? Now I need the lowest possible y value and the highest possible y value in this region. It's the lowest y value in this region. What's the highest y value? That would be the y value right there. What number is that? Aha. Remember, that's the equation y equals ln of x, and I know x is 2. So that's log of 2. The whole thing rests on rewriting the equations and then, to me, turning your head. What's the bottom, what's the top becomes what's the left edge, what's the right edge. And then what are the limits numerically becomes the lowest y value and the highest y value instead of the lowest x and the highest. Better? Now, because all I asked you to do was reverse the order, I didn't ask you to do anything. There's no function. I can't integrate. I think in the second one, 52, we actually have to do the integral because there are actual equations in that one. And if you look at 52, the way 52 is written at the moment is disgusting. Because the way 52 is written right now, I need integration by parts. But because it's square root y times sine y, that's even uglier because the integration by parts is not nice. I don't want to do that. Switching the integral makes that one a lot easier to do. Better? All right. More questions, ask me more stuff.
For 15.1 feet, it says use the midpoint, are we just supposed to like just try and find the temperature?
Yep. I think it is actually easiest if you physically draw on this picture. Because you've got 4 top to bottom and 4 left to right. So you cut it in half, you cut it in half again. Yes? So I cut it in half, I cut it in half again. I cut it in half, I cut it in half again. I'm sure the middle of my first box is this dark green color. That dark green color is between 32 and 28, so I might as well make it 30 there. And I can just estimate 16 different values. And depending on what you pick for your estimate, your answer might be slightly different than mine. I just want to see what you come up with.
Explain how they get the actual contour values, because
Sure, the contour values are actually numbered on the contours. It's a little hard to see. But here, for example, I've got this dark green color, and then I've got this lighter green color between them. And then I've got this slightly bluer color here. Well, that blue's got a 24 on it. So that contour says 24. It would be between 24, whatever the next number up is. You might as well use 24. Here, the contour next to this dividing line is at 28. 32 for this edge, and then 28 for this edge. So this color is between 32 and 28. You could use 32. If I'm over here, anything in this region is between 40 and 44. This dividing line here, going this way, goes from 44 to 48. From here to here, it's 40, right? So these are lower colors, and these are higher colors. You can use the numbers that are right on there. You don't have to estimate between them. But really, Mia, the best part is this picture is the state of Colorado. So is that one. This is the snowfall picture on the previous page. I know where the midpoints are. They even use the same number of boxes. So I can just say, I want this spot, put it on this color. I want this spot, put it on the other color. So I actually have the points I want, know where they're going to be. Because Colorado's a square, kind of. A rectangle. I saw a very interesting video. It turns out these borders are not straight lines. If you exaggerate the borders a lot, there are a bunch of natural contours to rivers and mountains and counties and things. Those lines are not perfectly straight. There are all sorts of wiggly, which have to be really, really exaggerated to see. I'll find a YouTube video. I'll throw it up on our Canvas page. Washington, D.C. was supposed to be square. It was supposed to be 100-mile square. And then Virginia backed out of the deal. So the part of DC that would have extended into Virginia goes along the coastline instead. It's supposed to be 100-mile square. There are actually markers, physical concrete markers every 10 miles. One of them's in somebody's front yard. Video. More questions, ask me more things.
Well, 15.1, do we just get a photo?
You can draw it in the grapher and then copy paste that if you want. You can try and make a stack by hand. You're welcome to do it anybody you see fit. I assigned that problem specifically for the goal of making you picture these things. Because again, the more complicated a region is, the harder it is to describe algebraically. I should at least be able to look at a picture and try and say, well, it kind of looks like this. Because I believe those shortcuts help in the long run. I think the advantage of that one is that the bottom's a rectangle.
Okay.
All right, it's 15.1. Yes, the bottom's a rectangle. More questions?
Draw the shape for 15.36.
15.36. So let's write the equations for the region. That means this is in R. 0 less than or equal to R less than or equal to 2 sine theta. And this is in theta. Pi over 2 less than or equal to theta less than or equal to pi. So I need the graph R equals 2 sine theta. Out comes the graphing calculator. What's that picture? Oh, look, I'm still in polar mode from when we did this on the other day. 2 sine theta graph. Aha! That's a circle-oriented on the y-axis, whose radius is 1, and whose center is 1. Diameter is 2. So now what I need to figure out is which part of the circle these angles describe. So what happens when you put in pi over 2? Yeah, but there are a couple of points there, so I don't know which one it is. What's r when you put in pi over 2? What's r when you put in pi? So that means we start there and go this way along that curve. Now you can actually trace this out on here. If I type trace and put in pi, not e, pi over 2, I see I'm up at the top of the circle. And as I move forward in theta, I go down the right half of the circle until I get to pi, and I'm at 0, 0. So that means the region I'm actually working out is that left half of the circle. Hey, wait a second. What's the area of the circle? But the radius of that circle is 1. So the area of that circle is pi. Which means the answer to this interval better be pi over 2, or we done effed up. Why do I know that? Because this is dA in polar coordinates. And the integral of 1 dA is the area of my shape. You know the answer to this even before I've done it. More questions? Oh, and Mia, because we're integrating r and we're plugging in the function, we're gonna get r squared in there, right? Means I'm gonna get a sine squared in my answer. Once again, I need that square reducing formula. I'm gonna see that an awful lot in these trig integrals.
That's the 1 minus.
It's either 1 minus or 1 plus because it's sine squared. I don't remember which is which, that's why I write it. I think sine is 1 minus, but I don't. I have to go through it the long way. 1 minus 2 sine squared. Yeah, so we want. Oh, I should use the same shortcut I used when we were talking about trig integrals in the first place. When we did trig substitutions, I said, when you see sine, you subtract. There you go. Thank you. I'll remember it now. X equals a squared minus u squared, or u squared minus x. Fine. More questions. Yes, Jeff.
For 15.326, I kind of just, like, in my mind, every time like starting it, I kind of forget, like, what to do when I'm given that, like that.
Okay, it says find the volume. Well, the volume is top minus bottom, and then integrate over the area. Ben, this is the one you asked, right? 26?
Yes.
Okay, so we've already drawn this picture here. But I've got a top surface, my paraboloid, and I've got 4 planes. X equals 0 is the YZ plane, Y equals 0 is the XZ plane, Z equals 0 is the floor. So I want above the floor inside the first octant, under this parabola. So I've got a roof that looks like this. Where's the outside wall? That's this one, X plus Y equals 2. Because that's got no Z's in it, it's going vertically. So now I've drawn this surface cutting into the paraboloid. I want the area under the paraboloid over this region.
Okay.
Volumes are roof minus floor.
Yeah.
You just have to figure out where the walls are.
Yeah, I don't know why I wasn't.
That's okay. It's okay. That's why we have the time. You can ask it more. That makes sense. We will see as time goes on, because I'm going to do triples at some point. We will see the difficulty becomes describing what our shape looks like. And everything we do in double integrals, generalize, not just the triples, but beyond. I have as many integrals as I need for the thing I'm working on. Now, most of the time I've used any integral with more than 3, it's been in probability theory. It's been joint distributions, and it's been basically, oh crap, I got to figure out what the hell this is. And in that case, because it's a probability, it's really a box from A to B. Okay, now from C to D, now from E to F, now from G to H. It's just how many variables are involved. It's ugly, but it's not a difficult looking region. It's just a lot of algebra, really. The other place I saw 4 quadruple integrals used was in a course that ended up talking about relativity theory. dx, dy, dz, dt. Okay, I get why they want to do that. And again, I don't want to deal with what those surfaces look like in 4 dimensions, so I'm not going to try and draw pictures anymore. I'm just going to describe them algebraically. It's a lovely discussion on those types of integrals. The book is titled The Nature of Space and Time, and it's a collaborative book by Stephen Hawking and Roger Penrose. I think it's about 20-ish years old by now. 25, somewhere in that range. I went to see Penrose give a talk at Pitt. And we ended up touching on something in that book, and then I had him sign my copy. So I have his autograph in my phone. Okay, more meandering, more questions. Jack, read that paper, the one that's on our Canvas page, the sketching impaired triple integrals. There's a lot of useful information about how to create the region's equations, even if you don't draw a picture. And if you don't want to draw pictures, that paper will help. But I like drawing pictures. More questions?
You think the bounds of your integrals was from the measure?
I did because I liked the picture. But what I can do is I can say to myself, the way to think about it is think about the equations with the most variables should be done first. So I've got one equation that's got all three. That's gotta be inside. That's gotta be here. I've got an equation in two, and then a bunch of equations in one. So this equation should be in the middle. And then the numbers should be the rest of it. Yeah, I work from more variables down to fewer variables. And if I'm just thinking about the region here, well, then this really wouldn't count, right? So this region, that's the region in the XY plane. This is going to be the first, it's going to be the inside. Whether I do it as type 1 or type 2, that one's going to be first. If I need to take that equation, if I want to do a type 1, I write it y equals. If I want to do a type 2, I write it x. And then I can say, oh, that's a y equals, I got to use it with this. That's an x equals, I got to use it with this.
For 15.326.
15.326. Which was this one. No, that's not right. 15.326 is above the cone and below the sphere. Right, okay.
Oh, wait, 21.25.
Paraboloids, you're right, I did look at 25. Bounded by the paraboloids, z equals something and y equals something. Z equals something, okay, wait a minute. Oh, okay. I'm gonna have to try and visualize this. Two x squared plus 2y squared. Okay. I'll do this without a picture. And then we'll try and make it work. That first equation, 6 minus x squared minus y squared, what shape is that? It said it was a parabola. The x squared and the y squared are subtracted. What direction does that parabola go? The bottom one, z equals 2x squared plus 2y squared, that's paraboloid. Which direction does that parabola go? I've got a parabola coming down and a parabola coming up. How are they going to intersect? There's going to be somewhere where those two meet, right? Paraboloid coming down, a paraboloid coming up. What shape should the intersection curve? It's a circle. If it's a circle, my bounds are going to be numbers. I'm going to have radius to radius, and I'm going to go around. You just told me it's a circle. What circle? The circle where those two things are equal. What do you get? And if I divide by 3, I get but wait a minute, I'm in polar. That's r squared. So I've got a circle whose radius is and if I'm doing the whole circle, what am I? 0 to 2 pi. Now, here's the best part. I can tell you exactly what this shape looks like, and you're going to laugh at me. Easter's coming. You're going to have little plastic eggs floating around, right? Think of the two halves of the plastic egg. And hold it with the narrow end at the bottom, and the wide end at the top. That circle where the two connect. I can even graph it. Let's get rid of the plane here. And we'll make that z equals 2x squared plus 2y squared. There's our upward opening parabola. We'll change this one to be 6 minus x squared minus y, come down out of the exponent, y squared. It's kind of hard to see here because I see too much of the outside parabola. So I'm going to go to the one that's going down, and I'm going to turn the inspector on, change that one so we can see through it a little. Right? I see the underside coming up. And then if I go to the other one, wait, I'll make that a little transparent. You see the top in there? Let's make the red one a little more see-through. No, the yellow one needs to be made a little more see-through. All right. There we go. Can't see the yellow one at all in there. Colors must be wrong. It's too hard to see. I've picked another color. Let's make it blue. No, that's the wrong one. Go back. Make this one blue. There it is in the inside. I don't know why I can't see it through. I used to be able to see through them. I don't know. But there you go. Now I can see the two connecting pieces. And look, they make a circle. We'll take that circle, which is at some height, and just drop it into the XY plane. There's a region in the middle. And again, it's top minus bottom. And now already theta. Instead of dx dy.
Why do you put the
The geometric argument is that even if theta stays the same, as I get further away, those two rays get further apart. Yes? As I move from the radius, from the origin outward, a little box here versus a little box here. Those have the same change in angle, don't they? But clearly the box that's further out is bigger. So I need to adjust for that, and the scaling constant that adjusts for that is exactly what the average rate is. What we will show in chapter 15, section 9, is we can look at the equations. And we can say, hey, those are a map from something in 2 dimensions to something in 2 dimensions, right? It's not a linear map anymore, like we did in linear algebra, but there's a matrix associated with this that measures the change in the shape from these 2 variables, x and y, to these 2 variables, r and theta. And if I measure that change in shape by looking at these functions through the method of what's called a Jacobian, will come out that will be that r. But I'm not there yet. It gets crazier when I get to triple integrals. Some of the Jacobians are really ugly looking. And then we can describe Jacobians in more general ideas. And they're very useful for these sorts of transforming. Not yet. Chapter 15, section 9. Okay. I have a problem with this homework. It's not a big problem. It's just a little problem. The problem is in my schedule. Let's look at tomorrow. They put the teaching demo right over this course, and I have to go to there. So what do I need you to do? I need you to email me your scanned homework. And we're not having class tomorrow. I've already recorded it. I've already put up the notes. It'll pop up right at the start of the class time, it'll be available to you all then, and we'll carry on Friday, but when you get done with this by class time tomorrow, please scan and email me your homework pages, and I'll print them and grade them like normal, all right? If you would rather come give them to me, catch me at some point and give them to me. I'm perfectly fine with that. Ideally, my morning class is downstairs, 9:30 to 10:50. It's in the end of the hall downstairs. You're welcome to drop by and give them to me there, or catch me at lunch or on golf course or something, but I prefer to have them before.
If we use Grapher, we just like put the screenshot and then
Absolutely. You can cut it and just stick it on there. Normally I'd tell you to print it out, but if you're not giving me paper, just include it in the scans. Thank you all very much, and I will see you on Friday.